Good evening. Today is May 12, 2024. Today we're going to continue talking about electrical field calculation. So last time we talked about electric field due to a point charge, but today we're going to talking about the electric field due to a ring. Okay, so the ring is actually kind of like a conceptual ring. The thickness of the ring is very, very thin, so that way we can ignore it. The charge the ring carries is Q, which is spread all over the place. And then the ring center is O, with a radius, let's call A. And then if we, from the center of the ring, to draw a line which is perpendicular to the ring, and then which is the distance B away from it. Let's call this point A. We want to find the electric field right here due to the whole ring, right? Because the charge Q is uniformly distributed along the ring. So how do we do that? Okay, so what we can do is we just take a very little piece of, let's say we call it dl. The dl basically is a little piece of the ring, and then the charge due to the little dl we can call it dq. And then if we look at the dq right here, let's say if we connect those lines, and then we notice the electric field is go to that direction. Again, we can put that into two components. One is X component, another one is Y component. Similarly, if we found another thing right here, and then we connect them, we'll find another, let me see, we will find another electric field due to that. Again, the X component is that, the Y component is that direction. Notice if we continue looking at these little elements, all the Y components, they cancel each other due to the symmetry. However, the X component is going to be superposition. So basically, what we can do is we use the little dl and then the little dq due to the little dl, and then we find the electric field due to that little dq, and then we found its corresponding X components. And then once we have that, we integrate the whole thing such that we will get all the charge around the ring, and then they will have all different electric field. They superposition each other. The Y components, they cancel out. The X component, they superposition. So that's the idea to do it. Okay, so let's divide and conquer. Let's look at the dq first. So the dq actually is equal to lambda times dl. What is lambda? Lambda typically we used it for the rate of the charge in the linear components. So this dl right here, since the rings they don't have a thickness, we can view it as linear. This is the lambda actually is the charge density. We know the whole charge along the ring is Q. If we use the Q divided by the total length of the ring, which is 2 pi a, based on the geometry, and then what we have is the charge density, which is called lambda, and then that times dl. Okay, so that's our dq. Now, based on what we learned the last time, if we treated this dq as a point charge, then we already know the dE is going to be k times the point charge, which is dq over r squared, right? That's what we learned the last time. The r actually is the distance between the dq right here with the point A, the point of the interest. Okay, now let's look at k again is the constant. dq is whatever this guy right here is q 2 pi a dl. But now we need to look at the r squared. What is the r squared? Again, since this x-axis, it is perpendicular to the ring right here. So actually this is a 90 degree. So again, according to the Pythagoras theorem, the a squared plus b squared is going to be equal to the r squared. So that actually is going to be a squared plus b squared. Again, we simplify this a little bit. We will have kq over 2 pi a times a squared plus b squared dl. Now we can find the E, the magnitude of E, which is the integration of dE, right? So it's going to be integration of the whole thing right here, which is kq 2 pi a squared plus b squared dl. Since k is the constant, q is the charge given, 2 pi another constant, a is the fixed radius of the ring, b is the distance from the point of the interest to the center of the origin of the ring. So everything right here is the constant. So what we can do is we just take out the constant. It's going to be kq 2 pi a squared plus b squared. So what we need to do is just to integrate the dl. Again, the dl is the little length, the little arc length of the ring. But if we integrate the whole thing, that actually is become a circumference of the ring, right? So we know this part, again, based on the geometry, is going to be 2 pi a. So we have kq, just copy the constants, 2 pi a squared plus b squared times additional 2 pi a, which is the whole integration right here. So this is the key to understand this problem. Because you know, once you integrate the dl, basically you try to find the circumference of the ring. So that's 2 pi a. This 2 pi a can cancel out with this 2 pi a. So what we have is kq over a squared plus b squared. Okay. So that's actually the magnitude of the E in that direction, right? But we know we need to decompose this into x direction and y direction. Y direction, all y direction cancel off, so we need to use the x direction. But the x direction, we need an angle theta, because that angle is equal to that angle. And then we have to use that, whatever the E we get times cosine theta to get the x component. So the EX in x direction will be E times cosine theta. And then E is this guy right here, is KQ over A squared plus B squared. But the cosine theta is going to be this distance over the hypotenuse. So this distance is B over hypotenuse. Again, due to the Pythagoras theorem, that's square root of A squared plus B squared. We can simplify this a little bit. So that would be KQB over A squared plus B squared. Because this actually is to the power of 1/2. Add this one, so total is 3 over 2. That's the power. Okay? And then, if we try to find the vector, because the vector is in the x direction, so we need to write down our final result E in the point of the interest A, and then since this is a vector, and then we know the components, the magnitude is that part, is KQB over A squared plus B squared, B squared inside, and then to the power of 3 over 2, and then in I direction. So that's our final result. One quick thing I want to remind you guys, what if the B is so far away from the origin, and then the whole thing can be viewed as the point charge, right? In other words, the radius A is going to be shrunk to 0. So if that is the case, if A is approximately to 0, B is very large, then the thing can be approximately written as KQB over B to the cube. In I direction, one of the B cancel out, so what we have is KQ B squared I direction. The Q is the whole thing right here, the whole charge. And then B is the distance between the point of interest and the location of the charge. So this is exactly the formula that we used when we're talking about the electric field of the point charge. That basically connects with the lectures that we had last time. So with that being said, that's all I want to share for the electric field. And next time we're going to talking about the different geometric form of the electric field. And then once you understand all those different different forms, you pretty much had a better idea about the electric field. Hopefully that helps you guys a little bit. Please feel free to leave the suggestion and question in the comments. I will try my best to help you. Thank you. Talk to you later. Bye-bye.